So it's another one of these occasions where we get 2 seminars for the price of 1. So 1 talk sort of streamed in parallel or attended in parallel by 2 groups of people. One is, of course, the GReTA seminar that you've all joined now, and the other one is the computing seminar of the School of Computing and Mathematical Sciences at Leicester. So we have a bit of a more diverse audience potentially today than we usually have, which is not a problem because Artur is well known in both areas. So he's been obviously sort of teaching and doing research in Leicester, and people know what he's doing there. And he also has a sort of a link, background in graph transformation. And I think we probably go back to the time when I think did I examine your PhD, Artur?
Yes, yes.
In Valencia a long time ago, and then we met again in somewhere in Brazil at an early ICGT, sort of I don't know 14 years ago or something. So he has a long history in graph transformation, like many of us. But his view is broader than that because he works on model transformation and model-driven engineering, and which will also come through, I think, in this talk. So yeah, without sort of giving sort of any more speeches by myself, let's sort of hand over to Artur.
Okay, thank you very much for the introduction, Raiko. The audience of this talk is indeed quite varied, and I'm going to try to keep everyone as happy as I can. With respect to graph transformation, my talk is mostly about applications, but I will also give some hints at the core notions that I have used. So let's start. On the slide, we see a number of examples of upcycling that illustrate the common understanding of reuse, which is the topic of this talk. In these examples, some well-known objects, which were ditched, have been put to work in a different context in innovative ways. Software reuse is a software strategy that builds new software systems on top of existing assets. Such assets were initially designed with a specific use case in mind, and reusing them involves putting them to work in a different context, as in the examples of this slide. However, some of these examples of upcycling given do not correspond well to the notion of software reuse. Software reuse of a given asset implies that its original function is not modified. We can enrich its structure or behavior, building new systems. However, if we retract the additions, we still get the original asset. Of all of these examples, we could argue that only the wellies keep its original function. We can put new wellies to work into different contexts without having to modify them. All of the other examples involve modifying the original asset, irreversibly changing its original function. In software engineering, reuse is driven by a need to cope with increasingly complex software while lowering software development costs, shortening delivery times, and improving software quality. As in the image, we build systems reusing other libraries and frameworks, including the popular web frameworks and libraries like the Apache Log4j library used for logging in multiple cloud applications. And this library was the reason for an important vulnerability that was detected last December in this infamous Log4Shell vulnerability, which enables a remote attacker to take control of a device on the internet if the device is running a specific version of this library, version 2. Common approaches to software reuse in software engineering are normally based on component-based software development, service-oriented architectures, software product lines, and low-code software development. I'm going to focus on this last one. Low-code and no-code software development epitomize current approaches to reuse-based software engineering, where software systems are designed using domain-specific languages so that they can readily be deployed on the cloud as a service, with little or no traditional coding at all. For example, Google has recently launched the Google Cloud Architecture Diagramming tool to transition from ideation to implementation with a no-code approach. With this tool, one can reuse a reference cloud architecture or start building a new architecture based on Google Cloud component. And once the parameters of these components are configured, the application can be launched on the Google Cloud. Correct engineering of such type of low-code platforms is critical to ensure the quality of the deployed software applications in order to try to avoid vulnerabilities as the log4shell one. The design principles and practices involved in low-code software development overlap greatly with those in model-driven engineering. For example, the structural semantics of DSLs is represented in terms of a metamodel and OCL constraints, and the behavioral semantics can be represented using graph transformations or model transformation operations, like, for example, model interpreters or model compilers. As low-code software development platforms become more sophisticated, such metamodel specifications and model transformations grow complex, and reuse techniques become vital for engineering them correctly. In particular, when those reuse techniques come equipped with machinery for verifying that reuse is performed correctly, it's quite beneficial. An example of a low-code software development platform for embedded systems is the Yakindu state chart tools. Yakindu offers an environment for modeling state machines, which can be validated syntactically and semantically using a query language that specifies structural constraints. And the modeling environment comes equipped with a mechanism for debugging state machines with a simulator. In the graph transformation community, such simulations are usually modeled via graph grammars representing in-place model transformations. And Yakindu also facilitates the generation of code for implementing embedded systems in different languages. For example, it supports C++ and Java, including the generation of test cases as well. Such code generation is usually implemented using model-to-text transformations or more complex model compilers that involve model-to-model transformations. In this talk, I'll present a semantic reuse technique based on model subtyping over metamodels to manage safe reuse in model-driven engineering of domain-specific languages that are a key component of low-code development platforms. The example that I will elaborate in more detail later on consists in an application operation S that applies a function to a domain set of objects. The semantics of these objects is defined in a metamodel, which may be enriched with OCL constraints, and the function will apply to elements of its models. I will explain this metamodel in more detail later on. The main aim of the talk is to present how we can reuse the application operation S safely across different domain-specific languages. And in the example, we are going to reuse this operation for simulating state machines. In particular, we want to reuse the specification of requirements in the abstract metamodel for specifying state machines, helping us to determine the class of finite state machines that we want to deal with. And in particular, we are going to focus on deterministic state machines. Then I will show how to reuse the function application operation in a different context for simulating those state machines. Reuse is achieved by a model subtyping based on model subsumption, which was initially introduced at SLE in 2017 for structural models, and it has now been generalized for metamodels with OCL constraints and for behavioral specifications of model transformation operations. In the talk, I'll provide an outline of the model subtyping operator and how it can be applied to several use cases. I'll start with a more detailed presentation of the example that I have just mentioned, and I'll cover the main contribution explaining the technical challenge that was faced to engineer the model subtyping operator. Here I'm saying engineering because the theoretical results that I'll present during the slides have been developed to produce an executable mechanism for reusing elements of the domain-specific languages. Afterwards, I will show an outline of the structural model subtyping together with a few notions that are needed to understand the approach, and I'll introduce behavioral model subtyping. Then I'll show the versatility of the model subtyping technique, referring to common use cases extracted from the research literature, and that I will also position a little bit this approach within the literature of the graph transformation community. This talk is mainly based on two of my articles presented at SLE and at SAE in 2019. A low-code development platform usually built atop a surface modeling language, like the state machine language we have seen in the Yakindu modeling environment. And the language is abstract, so that the language's abstract syntax is given as a metamodel, which may have additional constraints in OCL, specifying structural properties that need to be satisfied by the models. This metamodel specification, formed by a metamodel and its OCL constraints, characterize the structural semantics of the DSL. The metamodel specifications on the slide define modeling languages for abstract graphs and deterministic state machines, respectively. The top metamodel specification characterizes the graph of a function defined over nodes, and the also constraint defines the graph corresponding to a function, to a map. The metamodel at the bottom characterizes the state machines where transitions can be triggered by an event, and this event is indicated in the name of the attribute of the transition. Or these transitions can be triggerless as well, and in that case, they are completion transitions. And the specification of completion transitions is indicated with the OCL constraint. These metamodels also include notions for engineering the execution context of a model interpreter, namely the notions of mark to mark nodes that have already been mapped in the graph metamodel, and observation to indicate which states have been observed in a state machine simulation. In our approach, a metamodel specification denotes a model type corresponding to all valid models that conform to the metamodel and that satisfy its OCL constraints. And by using model subtyping, we are using the typical notion of model subsumption in type theory. And I'll explain two applications of this in this example on this slide. First, by showing that the state machine DSL is a subtype of the abstract graph DSL, the requirement that abstract graphs define maps can be reused in the context of state machines, where this requirement is translated as determinism on the representable state machines in that metamodel. Furthermore, in a second example, the subtyping operator also checks whether any additional constraints in the metamodel specification of state machines are compatible with the constraints on the graph metamodel, ensuring that the state machine metamodel specification is a valid structural refinement of the graph metamodel specification. In a second use case, we are going to consider behavioral semantics of domain-specific languages, and for that we're introducing an ATL transformation that defines a basic interpreter for evaluating functions defined according to the graph metamodel specification. This ATL is a rule-based language with which we can define in-place model transformations or normally out-place model transformations. These transformations could well have been defined using graph transformations using production rules. Just for reusing the example that is in the article, I have used ATL. I don't know if you're familiar with ATL, but although the actual details are not that relevant, let me just say that it's a rule-based model transformation language. In the rule on the slide, we take a node that has not been mapped, and we apply it by creating a new marking on that node. The rule also considers the order in which evaluation is performed, because we normally check the successor node of a node that has been marked already. I said that the actual details of the language that we use for implementing the model transformation or the graph transformation is not that relevant, because we are going to work on the interface of the operations, hiding the actual implementation details. So we could have our approach could well be used for graph transformation languages as well. To reuse the function application operation in a different context, we are going to use it to simulate deterministic state machines. On the slide, we can see one simulation step carried out by the ATL transformation applied to an initial state machine with an observation on the initial state. The simulation step adds a marking on the successor state with a new timestamp. The marking is an instance of the class mark of the graph metamodel, and because the ATL transformation is defined for the graph metamodel, it has no knowledge about the state machine metamodel. That means that we have to use type coercion in the last step to downcast the resulting state machine that is produced by the model transformation in order for it to be a valid model in the state machine metamodel. We'll explain how this is part of the subtyping operator later on, but this is another use case. In the previous use case, the interpreter is defined using the graph metamodel specification as its interface, and the interpreter is reused for this state machine specification as a black box. That is, the subtyping operator only guarantees that the entire space of size effects of the interpreter function within the graph metamodel specification is also present within the state machine metamodel specification. However, this type of reuse shows very little knowledge about the actual behavior of the operator of the model transformation. In this third use case, the specification of the interpreter is refined for an extension of the state machine specification by adding additional constraints that describe the actual behavior of the simulator of state machines. This slide shows a refined state machine metamodel that includes temporal information via the association predecessor. And in its metamodel, the classifier state machine corresponds to the snapshot notion, which contains a marker for the state currently being observed. In addition, each state machine may have one predecessor representing the previous snapshot in the simulation. The invariant specifies the behavioral semantics of the model transformation, relating the snapshot before the application, the transformation was applied, and the successor in the snapshot. At the bottom, we see the semantics of the model interpreter, consisting of two transformations given an initial state machine snapshot. In this case, we have a hierarchical state machine with two main states, each of them containing another state machine. The times we see here on this slide that, for example, in this trace, we have that first we evaluate this transition, and then in this following snapshot, we evaluate this transition. Whereas in the second trace, we have the opposite order. We first evaluate this transition, and we see the timestamp here, and then we evaluate the other transition here. By comparing metamodel specifications that contain behavioral semantics, the subtyping operation is also able to reason about behavioral properties of domain-specific languages, both to reuse behavioral semantics and to ensure valid behavioral refinement. Now that we have seen a few use cases of reuse, let me give an outline of how I approach model subtyping. And depending on how typing is considered, we can distinguish semantics where typing is where the typing relation is ontological, explicitly definable in the metamodeling language, or linguistic, implicitly defined in the metamodeling language. This second one is the usual approach available in programming languages when we declare variables with types. On the one hand, the semantics of object subtyping corresponds to the static subclassing, the typical generalization in the first approach, and it corresponds to subsumption in the second approach. Our aim is to build an approach where models are represented as graphs, where typing is ontological, so that they can also be manipulated as terms, where typing is linguistic. And why do we do that? On the one hand, graph transformation theory and well-known metamodeling environments like EMF, the Eclipse modeling framework, and the use environment for also constraints rely on the first representation, exploiting a set theoretical representation to implement tools and for checking model typing, and for analyzing also constraints. So we have tools there. On the other hand, type theoretic approaches like that rely on the second representation for exploiting inductive reasoning and higher order functions, and that's also quite helpful from a theoretical perspective. So our aim is to revisit the research question of whether type subsumption, the relation capturing that any inhabitant of a given subtype is also an inhabitant of a given supertype, is a valid mechanism for facilitating reuse in model transformation operations in MDE in order to analyze its advantages and limitations. In the following slides, I'll explain how we have defined the subtyping operator over metamodels, over metamodel specifications with also constraints, and over behavioral specifications. Let's start with model subtyping. To define model types for metamodels, we borrow the semantic domain from Cardelli and their work. We refine the semantics for type expressions as model type expressions in order to consider referential types that are not present in the type expressions that Cardelli defined, but that are present in metamodels. So here we see a metamodel defined as a class diagram, and here we see the model type expression that represents the same metamodel. It may seem that we're simply providing one more syntactic representation for class diagrams in order to represent the metamodel syntactically, like we could have used emphatic or planned UML. But in fact, we're using the type expressions that Cardelli defined in his work, and that means that there is this language is carries an ambiguous semantics as well. So whenever we represent model types in this way, when we define model type expressions, we are characterizing a model type formally. The extensions that we have added are to this language. So we have extended these model type expressions in order to be able to capture all of the expressivity available in Metamodels, and in particular, we are considering containment references, normal references that are not present in type expressions. We are reusing the expressivity for defining attributes, primitive types, and enumerations. And we also specify referential constraints, including the multiplicity, order, and uniqueness that were not present in the original model type expression language. And now we're going to have a quick peek at the definitions that allow us to specify the subtyping operator. I'll try to be as informal as I can. And if you want to see the full details, then please go to the article. The notion of model type, in our case, is the union type of object types defined in the model type expression, right? So we are simply characterizing each class as an object type, and then the model type is the union type of those object types. In the paper, as I said, in the paper, you can find all of the details of how these model type expressions can be defined. To achieve the operation of model subtyping, object subtyping by subsumption has been extended to model types. In fact, model subtyping emerges from the object subtyping relation, and it is implicitly defined when a pair of model type expressions are given. In this case, we simply have to check that the union type is a subtype. The union subtype is a subtype of the union supertype. The subtyping operator also contains potential circularities due to the inclusion of references when traversing, so due to the existence of references in a model. And what our subtyping operator contains an algorithm that can be found in the article, and what it does is to match structures without taking into account the names of the corresponding classifiers. So it's not based on a nominal type system, it's based on a structural type system. And what it does is to trying to find, so it uses an internal cache in order to break the references in order to avoid possible circularities, so that we can ensure termination of the subtyping algorithm. That was a very quick glance at the four concepts. So let me now build on them in order to deal with those constraints, which is the interesting part of this contribution. In the previous section, I have shown how we define model types as the semantics of model type expressions, and this gives us subtyping by type subsumption. However, if we want to consider OCO constraints, we need to deal with ontological typing as well, because and the main reason is that we want to use the tools that are based on that type of ontological typing, like use. And this also gives us access to a bounded model checker that we found quite useful for reasoning about the OCO constraint. So first, let's consider a metamodel as defined in a class diagram, which can be modeled in the use environment. Such metamodels have ontological typing, and their denotational semantics is described in Leicester's dissertation. And broadly speaking, a metamodel is interpreted as a set of graphs, as object diagrams. In my work, those graphs are mapped to terms that are typed with model type expressions in a very similar way in which we did during my PhD in Mod, as discussed with José Meseguer and also with Raiko when I was learning graph transformation theory. I was back then almost 15 years ago. And what we do here is when mapping the semantics of ontological metamodels to linguistic metamodels, we get model type expressions. It is quite trivial to construct a syntactic transpiler between metamodels and their model type expressions. So we assume that this exists and is given. Hence, we get a model type for ontological metamodels using our semantics via the mapping constructed on the right. So applying these two transformations. And we get so that in this way, syntactic model subtyping can now be applied to EMF metamodels. And we get semantic model subtyping to compare two metamodels. So this slide summarizes how I'm combining the best of ontological typing to reduce the tool use while still enabling the use of model subsumption, which we use for relating different metamodels that may not be related a priori, right? So here, remember that in the example, we are relating a graph metamodel with a state machine metamodel that have nothing to do, and our subtyping operator only takes these two metamodels as input. We are not, so the mapping between these two metamodels is learned by the operator itself. When we consider metamodel specifications with OCO constraints, the satisfaction of OCO constraints over models is taken from the original Richter's work, Richter and Gogola. And however, to check if there are inconsistencies due to the coexistence of OCO constraints of the model subtype and of the model supertype, we have to compute an extension metamodel from these two metamodels. The main purpose of this extension metamodel is twofold. On the one hand, it verifies the structural subtyping relation that is computed by the structural subtyping. And this structural subtyping relation is simply a generalization relation defined as class inheritance in the metamodel. And on the other hand, this extension metamodel also enables the analysis of OCO constraints so that we can apply the model finder that is embedded in use in order to reason about inconsistencies on constraints from different metamodels. Let's have a look at the synthesis procedure for obtaining this extension metamodel between two metamodels. Initially, we assume that the metamodels have no names in common. And let's assume first that if these, for presenting the construction, if there were names in common, we would need to apply some renamings first to the classes of the metamodels. First, we compute all possible multiple subtypings between classifiers of the subtype metamodel and of the supertype metamodel. This is done using the structural subtyping operator, which has multiple inheritance semantics based on the semantics of Cardelli. And remember that subtyping is computed based on a structure. So subtypings will be found even if names are not shared. So here we have, for example, that the state machine is a subtype of graph, but it's also a subtype of node. Why? Because they both have the same structure. They have this name. And also, they also have these features. These references are the same. Okay. Okay. In the second step, we apply the pull-up refactoring rule and extract virtual classes. A virtual class is a class that is not defined explicitly, and this is formed by the features that are common in two child classes. For example, on the slide here we have these two virtual classes that are extracted in order to refactor the name feature that is common to all these classes here. But we still have a problem. That's that the features in the subtype metamodel are still in there. So we need one more step. So virtual classes is a common concept used in programming languages to avoid the so-called diamond problem. That's when we have that a class may inherit two features from different classes that have the same name but different type, right? And there is an inconsistency there. And that happens because we have multiple inheritance semantics. So this step is to avoid that problem. And then in the third step, we apply another refactoring by pulling up those features that are still present in the subtype metamodel. And in this case, you see now that all these name features have disappeared and they have been integrated into this one, so that the metamodel that is produced has the appropriate semantics. When computing the extension metamodel, complements of the subtype and of the supertype metamodels are also computed. What are those complements? In the slide here, we see the state machine has stayed with the, so we see these two references, okay, here between these two references that we have between the state machine and the state, so perhaps not so obvious here, these two that are not present in the supertype metamodel, right? So this is a complement of the subtype, and is also produced by the subtyping operator. In this case, this is fine. So it's fine if we get additional features, additional structure in the subtype metamodel, because we are refining and adding information. However, if we find that situation in the supertype, it may be a problem because we want all of the object types defined in the metamodel to be extended. If we find a complement of the supertype that is not present in the subtype, that indicates that subtyping is not satisfied. When the structural subtyping operation infers several subtypings, we list the strict subtypings and rank them by giving priority to those typings that maximize supertype coverage. And then if there were too many, then the user would need. So we provide one by default, but then this is a step that the user may want to refine in case the tool was not very clever at choosing the default options correctly. So I will show a few additional examples later. Once we have the extension metamodel, we have the necessary equipment to reason about those constraints when applying subtyping. In particular, the extension metamodel is used to check the satisfaction of also constraints. That is by checking the constraints of the subtype, that the constraints of the subtype entail those of the supertype. If this property did not hold, we could have constraints that are satisfiable in the subtype, but not in the supertype, which is supposed to be more general. And this could be an inconsistency that our approach detects. In addition, this definition of subtyping with OCO constraints allow us to keep using type subsumption when using OCO constraints. This result is quite useful because it means that we can use our subtyping operator to verify structural refinement from a semantic point of view. The following slides, we extend model expression types, in this case for functions, to metamodel specifications in order to specify model transformation operations. When we talk about operation specifications, we are referring to operations that are declared for model types. That is, they may be declared using model types as input parameters and as return value, and for the return model type. In the third example of the introduction, we used an operation that simulates state machines. So model types are denoted by metamodel specifications. In this case, we have the metamodel for state machines, which also models the execution environment for the simulator. In particular, states can be observed, and each state machine object corresponds to a snapshot of the simulation, where it may have a predecessor snapshot. The predecessor relation refines this temporal relation between different snapshots of the simulation. The behavior of the operation is captured by an additional OCL invariant that checks that the predecessor of the last marked state is not marked. So in this case, this invariant is the behavioral constraint that defines the semantics of the operation, indicating well, we can read the also constraint in more detail, but in a few words, what it does is to check that this marking is not present over the state in the previous snapshot, right? Just ensuring that the effect has been enacted. To reason about operation specifications, I'll need the notion of extended operation signature, in which the model types can be represented as metamodel specifications, not just as metamodels. So that is whenever we define an operation, instead of typing the parameters with just the metamodel, we also take constraints into account, right? So this gives us much more expressivity in the language for defining model transformations. So that when the operation is applied on input model, the resulting model will conform to the target metamodel, and it will satisfy its constraints, right? Here, when we apply the transformation, we want to make sure that the generated graph is a valid graph in the semantics of the target metamodel specification. Syntactic subtyping for extended operation signatures. In here, so when we want to define, we want to check whether an extended operation signature is subtype of another one, then we need to use contravariance of the domain model types and covariance of the codomain model types, as usually done in type theory. And just to remind what that means, contravariance of input model types ensures that the operation can be applied to values of the subtype. And the covariance of output model types guarantees that the generated models will not create any problem in the expecting context.
Artur, sorry, Stefan had a couple of questions, which may be sort of still relating to this part. Stefan, you want to go ahead and ask directly?
Sure. So one question I think was about what your type relationship guarantees around executability, but I think that's comes in with the operation signature subtyping that you just introduced. Which I guess makes sense for outplay. If your operations implement as an outplace transformation, you probably you can specify that, right? But if it's an in-place transformation, how do you handle that situation where basically potentially the same model might be an input and an output model, and does your subtyping rule then basically just say, well, tough, you can't, your subtyping relationship must be an identity relationship, or?
Yes. Let me just mention that we are working with specifications of model transformation operations, which may not need to be executable. Okay, so these may be very abstract. They may specify requirements of the operations, and then we can make them more operational by adding additional behavioral constraints, right? So in a stepwise refinement process. I don't know if this addresses your point about executability of specifications of model transformation operations. And regarding the second question that I think you mentioned there is what happens with in-place model transformations. In this case, the model type is the same for the domain and the codomain. And the I'm not sure I got the question there.
No, well then, so does that then mean that the model types to which the operation can be applied are exactly only the model types over which it has been defined. So you can't have any subtypes of that because it's both an input and an output, basically.
Yes, but there, okay, very good. So in there, what happens then? Well, if you have the same specification, then our approach cannot, it will just tell you, okay, yes, it's subtype because it's the same operation and specification, right?
No, yeah, that's given. But what I mean is you lose the ability to have a refined subtype, to use a refined subtype, because only one of the two parts of your operation signature subtyping rule would be satisfied. Because if you've got a model type M1 and a model type M2, and they're different, then either M1 is a subtype of M2 or M2 is a subtype of M1, but not both of these conditions can be satisfied, and therefore your operation signature subtyping cannot be satisfied unless they are identical. M1 and M2.
Okay. So let me just mention that here I'm not considering the behavioral constraints yet. I introduced the concept in the example, but at the moment I'm just talking about signatures. The notion of extended operation signature only considers constraints for the model types, the input and the output. In the case that we have two operations for the same model types, it's okay because this is like less than or equal. So if we have the same operations, it will work. Now, let me continue with the next slide, and then we'll, if I don't answer your question, then you can ask me again. Okay, so there we go. with this, and thank you, Stefan, because this helps me now explain this notion of I can build on the notion of operation signature subtyping. With this, we can reuse an operation across domain-specific languages. And if you remember in the second example of the introduction, we wanted to reuse the operation used to apply functions to simulate deterministic state machines. For using operations, we only need to encapsulate a model transformation implementation behind its signature as an interface. And with the operation signature subtyping operation, we can find out that the state machine metamodel specification denotes model subtype of the graph metamodel specification. But that's not all. The operation signature subtyping operator also constructs extension metamodel, as I have explained, and that allows us to reuse the graph operation for state machines without having to apply any change to the operation. And that's particularly useful if we work with tools built atop the Eclipse modeling framework, because that's the interface that, and this is the type of metamodels that we use in our tool. Well, then we also need to update the signature of the operation in order to point to the extension metamodel, right? That would be the only change that we need to apply to the signature of the operation, but we don't need to change the implementation itself. The extension metamodel has learned all of the required relations between the two metamodel specifications, and it's what helps us reuse the operation as is. What's more, another advantage is that we can safely substitute the operation specification by another one as long as the subtyping relation is satisfied. This is useful when the operation specification needs to evolve. Okay, so now I'm going to try to address Stefan's point. So far, so good. But how about the last example where we want to refine operation specifications while guaranteeing that each extension preserves the semantics of the original version? For doing that, I need to talk about additional OCL constraints that specify the behavior of the operation, right? So we had constraints for the model, for the input and output model types, but now we need one more that will be, this will be an OCL constraint that is added to the extended operation signature, okay? Is at a higher level. From my point of view, such OCL constraints may fully specify an executable model transformation or not. The point is that the behavior of the model transformation is specified declaratively and in an independent way of the language that is used for implementing the transformation. We may start with a very abstract specification, and then we may make it more concrete as we add behavioral constraints to the point that it may even become executable at some point. A behavioral constraint has a temporal aspect and need to relate pairs of snapshots before and after the effect of the transformation has been applied, right? So there is a certain dependency here on how we specify the metamodel. An operation specification is then an extended operation signature that I presented in previous slides when we were discussing with Stefan, together with a set of behavioral constraints that we are introducing now, so that each pair of snapshots in the temporal relation satisfy the behavioral constraints. And that's what is specified here. Okay, so we want, sorry, here. Okay, so we want these pairs of snapshots to satisfy the behavioral constraint. An operation specification subtyping checks that the constraints of the subtype operation entails those of the supertype operation in a similar way as we have done for metamodel specifications, right? So when we have an operation specification subtyping, which is the extended signature together with the behavioral constraint, and we want to check whether one is subtype of the other one, then first we need to check that the signatures, one is subtype of the other one. So here, Stefan, this would be trivially satisfied if we are using the same domain and codomain. But then we have, this is the added part where we have to reason about the OCL constraints, right? The subtype constraint needs to entail the supertype constraint. And here, Stephen, would that answer your question?
No, I think it doesn't. I think it doesn't. I think what I'm understanding is that we're talking about slightly different things potentially. So I'm not sure whether that means my question is irrelevant or whether It just means we're talking across purposes. So my question was, and I've sort of added an additional comment in the chat to try and clarify that, was going back to your example thing, where your transformation basically creates a new mark object, doesn't it? In the graph model, right?
Mm-hmm.
And then you want to apply it to the state model. And what I'm trying to work out is, and maybe I've just missed something somewhere along the way, is what the condition is that tells you that you're allowed to apply it to that. And my understanding was that the condition is something about graph, something about state machine, the state machine metamodel being a subtype of the graph metamodel, or the state machine language, if it has additional constraints, being a subtype of the graph language. Mm-hmm. But then how does, so I can see how that ensures that your transformation can read everything that's in the state machine model, but it's not clear how that ensures it can write new stuff into the state machine model without breaking potentially additional constraints that the state machine model has introduced. Mm-hmm. And that's where covariance comes into play, right? That's why covariance is important, and why you typically differentiate input and output models. But if you're doing this for the same model, then you might potentially have only the one direction, and so writing a mark might be possible in the graph model, but in a similar configuration of the corresponding configuration of the state model, it may not be possible to write an observation. Now, I think in your case it probably is, because there are no refined constraints going on there, right? But it's easy. I think it's very easy to construct situations where it is not possible to do that anymore. And I think that was where I was trying to understand where that is caught in your setup, and I'm sure I've just missed something somewhere along the way. But
it's a good point, Stephen, and you are going ahead of me. So I think I'll try to address that point in subsequent slides, because we need a retyping step afterwards in order to downcast marks to observations in order to avoid that inconsistency that you have spotted. Regarding, just let me give some additional information regarding this example. This is the third example I have used in the introduction, and this metamodel is a refinement of the state machine metamodel that is compared with the graph metamodel, right? So we have two steps of structural refinement. We have first the graph, then and then its subtype is the initial state machine metamodel, and this is a second state machine metamodel that adds this predecessor association. That's the one that allows us to consider pairs of snapshots. And that's what allows us to define a structural behavioral constraint. Now, in this particular example, this works, as I was going to say later, but this works because in the second metamodel specification, there is no operation, there is no behavioral constraint. So adding one behavioral constraint will be trivially satisfied. So the refinement will be trivially satisfied. But when we talk about OCL constraints, we have to be careful. Are those structural OCL constraints? If so, we have to apply a structural subtyping. Are we talking about behavioral constraints? Then we have to reason about, we have to compare the behavioral constraint, right? So these are somehow separate. We have the metamodel specification, we have the operation specification. I have the feeling that the problem that you were thinking about refers to the coupling of these different types of OCL constraints. And I have to admit that at the moment, I don't see any issue. I would like to see if you managed to find a problem that I haven't managed to address, because it could be, it could be a case that I have not considered, but at the moment I don't see that example. So perhaps I continue quickly with the presentation, because I have, how many minutes left do we have, Raiko? 5 more minutes or so?
About, yeah. I mean, on the GReTA seminar side, we're a bit relaxed, but obviously the computing seminar should normally be around an hour, so 10 minutes in total from that point of view.
Okay, so let's wrap up. Now regarding tooling, these models, the subtyping operator has been implemented as a Java library that facilitates reuse in MDE. In our case, Metamodel specifications are defined as pairs consisting of an EMF metamodel and then also constrained in use format. And let me just show you the workflow of how our tool works. Given two Metamodel specifications, the tool will determine whether the first Metamodel specification defines a model subtype of the second one. If the check succeeds, the tool guarantees that the first model type is a refinement of the second one. Hence, any model transformation operation that is defined for the model supertype can be safely applied to models of the subtype. Going one step further, the tool also facilitates the reuse of such operation when it is based on EMF by using the extension Metamodel that I presented earlier. And this ensures that the application of the operation to models conforming to the subtype Metamodel specification without having to modify the implementation, which is quite useful. If the check fails, there are two main sources of incompatibilities. On the one hand, we have that we can have that the problem is in the metamodels, or that the model or the problem is with the constraints. In the first case, the tool points at the source of the problem by showing the classes of the supertype metamodel complement, those classes that are not extended by classes in the subtype metamodel specification. And if the problem is with also constraints, then we are using a model finder integrated with use that will provide a witness in the form of a model that conforms to the extension metamodel that shows how the constraints can be violated. And that's why, Stephen, I was mentioning earlier that I have an automated mechanism for refuting examples. So if you can find one, I'd like to see if we can spot it, because we have this model finder for it. Okay. Oops, I wasn't showing this part. So here we have that if the check fails, then we can inspect the supertype complement, and if not, then we are using the model finder and the integration with this model finder within EMF that was implemented in Totem MDE for getting witnesses. Yes, so just let me just mention a little bit more about, let me explain a little bit more about how to use the supertype complement. The supertype complement can be used for indicating the failures for the failure of the subtyping. And that information is quite useful to reuse operations when the supertype is only a partial type for the models of the subtype. The classes, so in here we have, for example, that in this example, we have the state machine metamodel, and we have in the initial in version 1, we have this observation concept. But let's say that we want to modify it and we remove this observation in order just to keep syntax for defining state machines. And this, now if we want to check if the version 2 is a refinement of the first version, it will fail because the observation is not there. So observation will be a concept that appears in the supertype complement. However, this supertype complement can be used to analyze the operations. In this case, we have an operation that is a model compiler using Fowler's notation for predictive printing the state machine. And we want to see if we could use this supertype complement to see if the operations appear in the implementation of the operation. If they do not appear, we can still apply this operation on the subtype. Right? So this supertype complement is quite useful to analyze whether we can still reuse the operations even though the subtyping failed. And now the topic about retyping that I mentioned to Stephen as well. So far we have assumed that subtype and supertype have disjoint names, but if that's not the case, the tool will rename the classifiers in the subtype to ensure this condition. And to reuse the operation now, we have two cases. First, if the classifier names of the supertype and the subtype are disjoint, then the operation can be reused as is. And when the implicit renamings are used, then we are going to need retyping of models. So retyping is implemented using the EMF synca in order to retype input and output models to and from the extension Metamodel. The EMF synca is a bidirectional synchronization tool between EMF metamodels that automatically matches their classes to migrate models between them. And the advantage is that it's quite handy for handling basic retyping, unlike the ones that we are dealing with now. The EMF synca will use the information about subtypings that is present in the extension metamodel to find out how the different metamodels are related. And retyping occurs by instantiating the most concrete classifier in a subtyping hierarchy. So when we are applying the simulation function to state machines, this simulation function that is defined for the graph metamodel, we first need to retype the input model to the extension metamodel, right? So there is a retyping there. Then we apply the transformation as is. And then we see here that we have a mark that doesn't belong to the state machine metamodel. And then we have to retype back by applying a back synchronization to the original metamodel, where the object mark is retyped with the corresponding object in the metamodel. That would be the observation. Right, and very briefly, perhaps I can comment on the relationship to graph transformation later on. I will cover this slide later on in the extended talk. Let me just conclude now. In summary, in this talk, I have presented how model subtyping has been generalized to metamodel specifications with also constraints and to behavioral specifications. And we have done this to facilitate safe reuse of requirements between modeling languages that need not be related a priori, and to ensure safe application of operations and to support substitutability and refinement of operation specifications, hence providing support for behavioral subtyping. This approach is quite generic and can be used to automatically verify model-based low-code software platforms, including behavioral specifications that need not be executable. Whereas model subtyping operator has been implemented on top of EMF and the use tool. And if you want to know more about the tools that I have presented in this talk, these are MD subtyping and the EMF synca. You will find more information about them on my webpage. And now, thank you for listening, and let me know if you have any question.
Okay, thank you very much for the nice talk. I mean, that was an impressive overview of a lot of work.
Thank you.
I had a kind of general question, and maybe then we can sort of go into details afterwards. But in your examples, but also maybe independently of that, it seems that if you have two complex meta models, and then you want to find subtyping relations between them, I mean, what are the chances that one is actually a subtype of the other? Because if you have two independently developed meta model, as you say, I mean, I would expect neither to be a subtype of the other in most cases. So, in the sense that I would imagine subtyping to emerge if you somehow derive one from the other in some way, but not completely sort of accidentally. But I mean, obviously, I haven't analyzed this. So, what are your experiences there? Do you have examples of meta models that have been developed independently and where you found subtyping relations?
Yeah. So in this case, I think that this type of reuse is driven by the type of functionality that is it's driven by the context where you want to reuse the operation, right? So when you think about reusing a particular tool in a context, it's because you see certain similarities there. Otherwise, you wouldn't have thought of reusing that operation in that context. That may give you some hints on how the data structures that you're using may be related in some extent. Because otherwise, if the two software artifacts that you're dealing with are completely separated, it's very unlikely that you'll think about reusing functionality from that context into another one. So I would argue that that is the context what drives the reuse. Regarding the specific case studies, this future work, I'd be interested in looking at, for example, reusing functionality built for state machines in different contexts. For example, for simulating digital twins, in different case studies. In there, it's very likely that perhaps there is a common core of the state machine that kind of facilitates those similarities that can be exploited, even though you are dealing with different specifications of state machine, right?
I mean, just by analogy, and I'm not sure how true this is here in this domain, but in software engineering in general, in, let's say, component-based systems, and so the experience is that you need to design things for reuse rather than hope for reuse to emerge sort of naturally. So that means you have component frameworks, for example, that are sets of components that cover, think of it as a library, component library, that are designed in such a way that they are sort of as flexible as possible and can be sort of incorporated into bigger applications easily to essentially to be reused. And it's difficult, even if it's possible in principle, to reuse things that are not made for being reused. So that's the kind of, and I guess the question is, I don't know whether that's specific to the reuse here is of course different in a way, because in cases of components or libraries, you probably have more encapsulation than you have here. So here you're basically reusing a complex data model. The Metamodel. So I don't know whether that makes it more difficult or easier.
Yeah.
But it's certainly different from reusing essentially an API in a sort of more traditional software engineering context.
Yes, but I would argue that this approach subsumes that one as well, in the sense that you may have a black box component implemented with an interface that is given by its signature and the behavioral specification. And then you extend that one. You want to check that the extension is correct. That's what can be done. The advantage of this approach, by saying that the two metamodels need not be related a priori, means that you don't need to specify those relationships manually as you would need to do in other approaches. That's inferred automatically. It is true as well that we can try to find unrelated metamodels, try to find similarities between unrelated metamodels, but yes, the chances are less than if you drive that reuse, of course.
Okay. All right. But maybe this doesn't actually, maybe it's not mutually exclusive in a sense that the idea of designing for reuse obviously needs a foundation that you need to check whether something that you have designed for reuse is actually reusable in a particular situation. So in a sense, maybe you have the sort of the type theoretic underpinning, and then there is a methodology on top of that to use that in such a way that it actually supports reuse kind of from a pragmatic point of view in specific situations. So maybe what I was missing, I guess, maybe is the kind of reuse methodology on top of the technical mechanism for reuse. To understand the kind of how that would work in practice. But I appreciate that we have to maybe have the mechanism first and then the methodology on top of it. Okay, cool. Thank you. Sorry, any other questions? Stefan has to go. Stefan seemed to be happy in the end. Maybe I have another question then. So what is the computational cost of doing this? So there's one that on the structural side, you translate the models essentially into this type specification, and then so effectively, isn't that almost a sort of logical inference problem? Because you have to show that the constraints on one side imply the constraints on the other side. So that is computationally feasible in general, isn't it? If you have a first order logic or more sort of specification. So how do you do that?
The computational cost here is given by the bounds of the model finder. We're using a bounded model finder in order to try to find a witness of an inconsistency. So we actually have a semi-decidable procedure. It becomes decidable up to specific bounds. right? So the greater confidence you'd like to get on the results, the more costly it will be, because the larger the search space is going to be. So that's the main bottleneck of the approach. But on the structural side, the structural subtyping, I don't have the complexity analysis, but it's from the experiments that we have performed with reasonably large metamodels, it's quite fast. It's the also constraint side what drags the performance a little bit.
Okay. Yeah. I mean, complexity analysis is another question. I mean, the question really is what works pragmatically and what doesn't work, because as you said, it's in general it's semi-decidable. So it's not you can't put a complexity bound on it if it's semi-decidable. Or the question of what you can do. Okay, cool. So are there any other questions? Otherwise, I would suggest that we close the formal part of the meeting now. And anyone who wants to stay with us can do so, obviously, on the Zoom channel. But we're going to shut off the live stream and basically be within a smaller group here just for a friendly chat afterwards. Yeah.
Mm-hmm.
So thank you very much again, Artur, and
my pleasure.
Nicholas, are you doing the honors of